Welcome back everyone to this module on search in constraint programming and with MiniCP. So without further ado, let me tell you what we're going to do this week. So first thing, I'll motivate the work. I'll tell you what we're going to look about and what heuristics such as variable and value selections heuristics are, as well as strategies like discrepancy search and restarts that try to offset the weaknesses that heuristic might have. So without further ado, let's get going. Now, the first thing I want to do is actually tell you about the fundamental paradigm that we're adopting in constraint programming, which is one of model and search. And search is where we focus today. Now, there are two distinct approaches or school of thoughts, as you might think, to actually look at search. The one is about open search. The other is about black box search. Now, how do they differ? Well, let me tell you. Open search is about the ability to write custom search procedures that take advantage of your problem in order to be able to crack a very hard, difficult problem that you wouldn't be able to solve otherwise. So that's very important to be in a position to write concise and effective search procedures if you buy into that philosophy. The other one is black box, where the idea is that for many problems, they're pre-made searches that will be quite effective, and there is no reason to go ahead and write a custom search procedure. You might instead simply adopt one of these canned procedures, and it should work quite well. Now, this is a line of thoughts that has been ongoing since the mid-2000s, and it's been quite effective. So we'll look at a number of options along that space. Now, before I start, let's refresh our memory with an example you've already looked at, the n-queens problems. So this is the code you've seen before, and what I'm purposefully ignoring here is this part, which is the model. What I focus instead is on this block, which defines a search procedure that uses depth-first search as a strategy, and then it uses the code in the blue box, which is what we called the branching scheme. Now, the job of the branching scheme is to actually address three issues. The first is, how do we choose a variable? And in this colored box, we find a code that picks a variable. Now, if we didn't find any, we would return an empty branching scheme, which means we're at a leaf of the dynamically constructed search tree, and we could report the solution. Now, if there is still a variable to branch on, we go into the else part, where we pick our variable, in this case qi, and then we do the second heuristic, which is choosing a value. In this case, it's a simple choice. It's picking the smallest value in the domain. Now, once I have the variable qi and the value v, I can actually do my third selection, which is the branching scheme. And the branching scheme here is one that simply is binary. I have two choices. Either the queen I is equal to v, or it is not equal to v. And I represent both options by closures, as you see that, one and a second, and I package the two closures in an array of procedures, which is my branching. So this effectively has created this structure, which is a node of the dynamically constructed branch and bound tree, or branching tree, and we're going to reapply that scheme until we hit a leaf and all the variables are fixed. That's the basic idea. So fundamentally, our choices for variable selection, value selection, and branching are many. We could decide, just like we've done, to decide that a variable is equal or not equal to a value. Notice that the union of the two options is covering. It's still the full domain. Or we could split, say that you're greater than the value or less or equal to the value. Or we could even enumerate. There are lots of options, right, for how we do that branching method, and we're going to look at some alternatives. Now, what's important to realize, of course, is that these branching decisions do have a strong impact on the size of the search tree and therefore the search effort that we have to do in order to find a solution, or an optimal solution in the case of optimization. Why is that? Well, that's because it all impacts the tree. It will impact its size, its shape, the depth at which we find solution, as well as their location within the tree. So for an example, here are two trees. There is a tiny little one and a big one. And of course, the question that I put in front of you is, which one would you rather explore? The large one or the small guy? And of course, you know I'm playing with you here, right? You'd prefer to explore the small tree because it's a lot less effort to find a solution or to prove that none exists. Now, the reality is that depending on which variable you branch on first, the propagation that's going to shrink the domain of the variable effectively shrink the size of your tree. So by making good choices early on during the search tree exploration, you may have a big impact on how big the tree is. So that's one of the reasons why you should be careful with your variable selection heuristics. Now, the second thing is that you might find out that solutions are very deep in your tree or very shallow in your tree. And of course, you'd like, if you want to find a solution quickly, you'd like to stumble on this solution first. So this tiny little tree that's shallow should be to the left of the deep tree so that you hit this solution much more quickly than the other one that's very deep in the entire structure. Now, of course, a third issue is that sometimes if you have a tree that's even of a given size, a solution is just sitting at the far left of the tree, which means that there is a simple path leading to it. Follow your heuristic and you will straight down, never backtrack, fall on your solution here. Now, that may not be the case. It may happen that the solution is not there, but way further along the tree. And it might be very difficult to reach it, which means that the path that you trace to get to that solution has a lot of turns, left and right, and it's not obvious where it is. It's a hard to reach solution. So you want to be careful, because when this happens, how do you compensate for that, right? The heuristic should place solutions on the far left, but every now and then they will be further off. What's a way to compensate? That's where strategies come in, and we'll discuss that as well. Now, bottom line is that your variable selections will have an impact on the size of the tree, on the quality of the solution you produce, on where the good solutions are. And the same can be said of the value selection, right? It plays also on the size of the tree, on the location of the solution to place them as far left as you can if this is a possibility, or on the quality of the one you find. Strategies are a way to mitigate weaknesses of your variable and value selection heuristic in the case that you have solutions that are hard to reach, or that good solutions are hard to reach. You'd like to actually be able to look around in the tree a little bit more flexibly and not necessarily follow that first search approach. We'll talk about that too. Now, if we look ahead for this week, what we're going to do is variable selection, then value selection, branching selection, and we're going to start at the very first natural place, variable selection. But for that, I'll see you in the next video. See you next time.